In this video, we're going to discuss equilibrium as it applies to solubility, and that'll allow us to better understand how temperature can affect a solid or a gas's solubility in a liquid. So let's start by looking at dynamic equilibrium for solubility. So we're going to be looking, when we talk about equilibrium here, at the two different rates of that are occurring within the system. The rate that the solid is becoming dissolved in the liquid. And so if we're thinking about an ionic compound, that means that a little cation or anion is being surrounded by water molecules and separated from the solid and becoming part of the solution, the liquid solution. So we have the rate of dissolving, or the rate of solvation, you might see it called. And then we have the opposite, which is the rate that ion from the solution will reform part of the solid. So it'll be floating around in the water, tumbling all over the place, and then it'll come to the solid and it'll be captured by the intermolecular forces of it, and it'll stay put with the solid. And that's going to be our rate of recrystallization. So initially, when we have just dump some salt, and this is sodium chloride in our example. If we look at these two pictures on the screen, initially, like right away when we dump it in at time equals 0, we have a lot of solid right at the bottom of our beaker. And over time, as time progresses, that gets smaller and smaller and smaller until we have a much smaller pile. And so what's initially happening is we have a very high rate of dissolving because we have a big pile of solid and absolutely none of those ions are in the water, right? And so the water comes in and it starts surrounding our ions. Uh, and so it'll dissolve faster once we initially add it. But then as ions build up in the solution, that rate of dissolving or rate of solvation will slow down. Um, and so as that rate decreases, as we have more and more and more of these ions already in solution, we see that we start having our other opposite rate, the rate of recrystallization, start to increase. As more and more and more of these ions are in solution, as their concentration increases, then the salt can start to recrystallize onto the solid, the ions that are present in solution. And it's slow at first. And as the concentration of ions increase in the solution, that rate of recrystallization increases. Now, that rate of dissolving, which is really high initially, is going to start decreasing as our rate for recrystallization, which is initially 0, starts increasing. And dynamic equilibrium will be reached when those rates are the same. And we won't see the volume of salt or the amount of salt on the bottom of the beaker change. Now, change is constantly happening. It's constantly seeing particles from the solid dissolve and ions from the solution recrystallize. It's just that it's happening at the same rate. So we don't see a macroscopic change that we can observe. And that's dynamic equilibrium. The dynamic part is that change is occurring. Like we're still dissolving and we're still recrystallizing, but the equilibrium tells us that we're not going to observe an overall change. And so when we talk about how much of something is dissolved in a liquid or any sort of solution is formed, we have a couple terms that apply to this and that connect to equilibrium: saturated, unsaturated, and supersaturated. So a saturated solution is going to be when the solute and solvent are in that have hit dynamic equilibrium. So the rate of recrystallization and the rate of dissolving are the same. So we're already at that perfect equilibrium. If I add more solid, then it will not dissolve because my rate of dissolving would need to be higher. Now, unsaturated means that we haven't hit that dynamic equilibrium. So there's less solute has actually dissolved than in our saturated solution. So we haven't hit dynamic equilibrium. There's still a higher rate of dissolving than there is a rate of recrystallization. So that rate of dissolving is higher. So if I add more solute to it, it will actually dissolve because it will keep dissolving and dissolving and dissolving until that rate of dissolving and recrystallization is the same. Now, supersaturated is when we've passed dynamic equilibrium. We've actually dissolved more solute than we would see dissolved at equilibrium. And so, if I add more solute to this solution, suddenly a lot will fall out into the bottom of the beaker. So, we'll see a sudden recrystallization that occurs throughout the entire solution. Um, and And usually, supersaturated solutions need a lot of stillness to form them, or you need to apply heat. So, a great example of a supersaturated solution is simple syrup, right? We heat the sugar and water to a higher temperature to increase its solubility, and then we slowly cool it, and it remains a supersaturated liquid. If I were to drop a sugar cube in it, sugar would start crystallizing on that cube right away. And also you can see in your supersaturated solutions that you start forming sugar crystals on the surface after not too long at all. And so these are our different terms that we're going to use for um, talking about solubility and equilibrium. And I think that the most important is that saturated means you're at equilibrium, which means that you're going to have solid on the bottom of the beaker or floating around, and you'll also have the solution.